Dear students, we are resuming our discussion of physical quantities and units today. Let me quickly do an overview of what we have already covered. We talked about physical quantities, we define what physical quantity is. It is a measurable feature of any physical object. It could be its length, its area, its volume, its mass, or anything that we can measure. Then we discussed the subdivision of physical quantities into two broad categories: base types of quantities and derived. In base quantities, we mentioned 5 physical quantities, which include time, mass, length, temperature, and electric current. And I emphasize that we need to remember the symbols of their units in which they will always be expressed. Time is always in seconds, so it's written small s. Mass is always expressed in kilograms, so we write kg. Length is always expressed in meter, so we write small m. Sometime in the statement of the question, instead of the word length, displacement is written. Even then, the symbol for the unit will remain the same. Sometime it's radius, sometime it's diameter, sometime it's height, its depth, its width. All these things means we are measuring length, and we always express this in meters, so the symbol will remain small m. Temperature will always be expressed in Kelvin, and that is capital K. And electric current is in amperes, so capital A. And with this background, we discussed various derived units, and we learned how to express these derived units in terms of base quantities. Like there are several derived quantities starting from area, volume, density, speed, acceleration, force, pressure, work, energy, and so on. We mentioned the derived units in terms of base quantities, and we learned at least 3 things about derived quantities and how we express these derived quantities in terms of base quantities. Let me mention all those 3 things one by one so we know what we covered yesterday. Number 1, sometime we are given a quantity and we are asked to express it in terms of its base units. Let's say pressure. Express a physical quantity, by recalling its defining equation. By recalling its defining equation. For example, if I ask you to express pressure in terms of base quantities, which are also known as dimensions of pressure, we must recall the defining equation of pressure. which is simply force over area. That means the basic requirement of this type of question is that we must be able to recall what pressure is defined as in terms of other quantities. Pressure is force over area. Force is kilogram meter per second square divided by meter square. So when I simplify them, it becomes kilogram m minus 1 s minus 2. So this is pressure. This is one type of questions that we discussed yesterday, that just by recalling the defining equation of any quantity given, we can express it in terms of base units, which are known as its dimensions. So dimensions of pressure are kilogram meter minus 1 second minus 2. So these are dimensions of pressure. Second type of questions were those questions in which an equation is already given and there is an unknown quantity that you have to identify, and you don't have to recall any defining equation in it. For example, what is this equation? What is this relationship? Density multiplied by speed square. When density is multiplied by speed square, a certain physical quantity is obtained, and it is not easy to identify just by looking at this product. But when we express density in terms of its dimensions, when we express speed in terms of base quantities, the dimensions again, then we simplify and see what quantity it comes out to be. And sometimes it is surprisingly simple, which it doesn't seem to be in this form. Density is kilogram per meter cube, whereas speed is meter s minus 1, and it is squared here in this formula. When we further simplify, it becomes kilogram. Can quickly express them in their dimensions, but sometimes they just give us a product of different quantities and they want us to identify what it comes out to be, and we simply express them in their base units, and we see finally in their simple form that it is a familiar quantity, sometimes very simple one, and in this case it is pressure. There is another type. We also discussed it yesterday, and that was to determine unknown constants in an equation which is known to be correct equation. An equation which is correct in physics is referred to as homogeneous equation. I'll come to this definition shortly in this lesson. What is a homogeneous equation and how sometimes we show that an equation is homogeneous. But if an equation is known to be correct, it's a physical equation, experimentally verified, known to be accurate, how do we calculate or how do we identify any unknown constant in that equation? For example, in this equation, F is equal to G m square over r square. I discussed it yesterday. I'm revising it just to know what is this type of questions. This is a constant that we don't know. And in order to know this, I express force, I express this mass, and I express this distance in terms of base units. Force is kilogram meter per second square. This G is written as it is because it is to be found. Mass is kilogram, or it is squared, and distance is expressed in meters, so it is squared. When I simplify all this, this G will become kilogram minus 1 meter cube and S minus 2, and this is the dimensions of G. And as I emphasized yesterday, it is not necessary always to express them in a familiar, in a known form. Sometimes it can be a very unfamiliar, totally weird kind of expression, like this is kilogram minus 1, which is unusual, and meter cube S minus 2. So we don't know exactly what quantity it is, but the dimensions are considered correct as long as the mathematics of this equation is fine. So these are three important type of questions which appear in the exam related to this topic, which is expressing quantities in terms of base units. Another important use of expressing derived quantities in base units is to find the powers in an equation which is known to be homogeneous. But let's first define what is a homogeneous equation. A homogeneous equation is the equation in which all terms can be expressed in terms of same base units. For example, if pressure is force over area, the two sides must have same dimensions in the end when expressed in terms of base quantities. This is kg m minus 1 s minus 2, and when this all simplified as I did on that side of the board, this is kilogram m minus 1 s minus 2. All this simplifies to this form. So if we have same dimensions on the two sides of the equation, then the equation is said to be homogeneous. Similarly, F is equal to ma is homogeneous because F is kilogram, m minus 2, and this is kilogram ms minus 2. So it is homogeneous. But there could be a more complicated kind of equations, and let's have an example of that type. Sometimes an equation has more than two terms. For example, pressure could be expressed in terms of density and speed square plus density into acceleration due to gravity into height. This is one equation that we study in fluid dynamics. If all these quantities are known quantities and we express them in terms of their base units, we see that every single term comes out to have same dimensions, which is pressure. So if this is pressure and the dimensions of this term is also pressure and dimensions of all this term is also pressure, then this equation is homogeneous. Let's see quickly how it happens. Kilogram, meter, minus 1, s minus 2 are known to be the dimensions of pressure. This is 1 over 2 rho v square. Rho is density, this is speed, and this is 1 over 2 is constant, so we ignore it. Density, however, is kilogram m minus 3 multiplied by ms minus 1 squared. And when I simplify it, it becomes kilogram meter minus 1 s minus 2, which is same as pressure. Similarly, this term, which is density first, kilogram meter minus 3, which is density, into this is acceleration due to gravity, so meter per second square. This is height, so meter. When I simplify them all, it again becomes kilogram meter minus 1 s minus 2. So same dimensions in all three terms. So any equation in physics which has same dimensions, which can be expressed in the same base units when simplified to its final form, this type of equation is said to be a homogeneous equation. Now, sometime it is stated in the question that the equation is homogeneous, but there are certain unknown quantities, certain unknown numbers in that equation that can be determined, and let's quickly discuss how we do it. Suppose we know that this equation is homogeneous. Energy is equal to mass time speed. But we don't know what is the power of this speed. We know m is 1 raised to power 1, but we don't know whether this c is raised to power 1 or 2 or 3. So this n is unknown in this homogeneous equation. This is a homogeneous equation, which means the two sides of the equation must be expressed in the same base units. So this is energy. So kilogram meter square s minus 2 are the dimensions of this quantity, and on this side we have kilogram because this is mass, and this is meter per second because this is speed, and this is raised to the power n. If I further simplify it, it becomes meter raised to power n, and this second raised to the power minus n. If I compare the two sides of the equation, it can be easily seen that meter is raised to 2 and meter is raised to n. So comparing the powers, on the two sides, we can easily see that n must be equal to 2 because m is 2 here and m is raised to power n here, n must be 2 if this equation is to be homogeneous. Similarly, s is raised to power minus 2 and s is raised to power minus n. Again, n is equal to 2 if this equation is to be homogeneous. So in homogeneous equations, it's easy to see what is the power of a quantity if it is unknown power, and this is done by comparing the powers of the base quantities, the dimensions of the physical quantities in the homogeneous equation. So this completes one part of our discussion. This completes the discussion on the physical quantities, the base quantities and derived. We can move on to our next topic now, and that is about the prefix. Sometimes we express our quantities in very, very small uh, small amount is expressed in that quantity. Sometimes a very large measurement is expressed in terms of these quantities. For both of these extremes, we have defined certain prefixes so we can express these quantities in a simpler manner. Let's have an introduction of that. Eraser. Board eraser नहीं मारा. अभी है टाइम. Sometimes we have to express very small measurement in terms of those units which are used for expressing extremely small quantities. For example, in order to express 1/100th of a meter, we use the prefix centi. Its symbol is small c, and it is 10 raised to power minus 2. That means 1/100th of the meter if the quantity is centimeter. And since it is written before this meter, that is known, it is known as the prefix. So this is the prefix used to express smallness of a measurement. Centimeter means 1/100th of a meter, but sometimes it could be even, that is milli. And this is small m. It is 10 raised to power minus 3. And when written along with the meter, it is read as millimeter. So both are small m's, but this is for meter, and this is the prefix milli. So millimeter. And if the measurement is even smaller, 1/1,000,000th of a meter, it is micro. Micro is always written as mu. This is a Greek letter, mu, M-E-U. And this is 10 raised to power minus 6, which means 1/1,000,000th of any quantity that is being measured. If it is length, it could be micrometer. If it is charge, it could be microcoulomb. If it is time, it could be microsecond. So all the quantities which are measured and they happen to be very small, it is useful to express them in terms of these prefixes. So it saves our zeros. Sometimes we have to write it as 0.000. For example, if I do not express it in this way, let's say 2 centimeter is 2 into 10 raised to power minus 2 meter. It could be written as 0.02. In this case, it is 0.002 if it is 2 millimeter. But in this case, it becomes 0.000 0, another 0, and then 2. So as the measurement becomes smaller, it becomes inconvenient to write it in this way, and it is much easier and more convenient to express in this way, and that is why we use prefixes. The next one is nano, and this is 1/1000th part of the unit in which some quantity is being measured. Nano is written as small n, and it is 10 raised power minus 9. It could be nanometer, it could be nanocoulomb, it could be nanohertz if it is frequency, it could be nanosecond if it is time. So 5 nanometers simply means 5 into 10 raised power minus 9 meter. This is 5 nanometer. And if I do not write this here, I have to write 0.00000005. One dot followed by 8 zeros, and then 5 would mean 5 into 10 is minus 9 meter, and that would be highly inconvenient. So this is a more useful way of expressing it. And finally, after nano, we have pico, and pico is small p, which is 10 raised to minus 12. And this could be picometer, picofarad, picohertz, picosecond, and so on. So this is one set of units which are used to express very, very small quantities. There is another extreme in which we express those quantities which are very large. Sometimes very large distances are involved. Sometimes time is expressed in very large numbers. Sometimes it is years are expressed in terms of seconds, and the number becomes very large because it becomes billions of seconds then. And in that case, we use the other set of prefixes which are known as multiple units. Multiple units, as I said, are used to express large quantities, and this we can start with kilo. Kilo is small k, and this is 10 raised to power 3, and if I write kilometer, that simply means 10 raised to power 3 meters. That means 1000 meter. That means this is a convenient way of writing how many meters are involved. Instead of writing 3000 meters, we simply write 10 raised to power 3 meter or 1 kilometer. Then we have mega. Mega is capital M. This is 10 raised to power 6. It could be mega seconds. It could be mega meter. It could be megahertz, and so on. Then it could be giga, which is capital G. It is 10 raised to power 9, and this is gigahertz, a very familiar term in computer. Gigasecond. If seconds are expressed in terms of, if years are expressed in terms of seconds, sometimes we have very large number, and gigasecond is helpful to express that number. And then finally it is tera, which is capital T, and it is 10 raised to power 12, and this is terahertz. Tera seconds tera, meter, and so on. These are multiple units. So you see the difference. This is the kind of prefixes which are used to express very, very small measurements. 0.000000 type of numbers are expressed in these prefixes, whereas very large number, for example, 3 followed by 6 zeros, 5 followed by 9 zeros, or 12 zeros, they are conveniently expressed in a compressed form just by writing 10 is power 12 instead of writing 1 followed by 12 zeros. So this is about the prefixes, and we close today's lesson here. More of it tomorrow in the next lesson, I mean, with a few practice questions. Thank you.